Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 23 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 1976. Number of ways to arrive at destination. Okay, so let's read the problem statement first. You are in a city that consists of n intersections numbered from 0 to n minus 1 with bidirectional roads between some intersections. Okay, so see this example number 1, n is 7. Okay, so n is 7 simply means that we have intersections from 0 to n minus 1, that is 0 to 6. Okay, so here in this graph you see we have vertices from 0 to 6, 0, 1, 2, 3, 4, 5 and 6. Okay, done. Now the inputs are generated such that you can reach any intersection from any other intersection, and that there is at most one road between any two intersections. Okay, so here see in all these intersections there is at most one road only. Okay, so here 0 to 4, okay, you see these two intersections, there is just one road. From 0 to 6 there is just one road. From 4 to 6 there is just one road. From 3 to 6 there is just one road. Okay, so only one road is there, right? Now after that you are given an integer n and a 2D integer array roads, where roads of I having u, v and time means that there is a road between intersection u and v that takes time, minutes to travel. Okay, so here 0 to 6 time is 7, 0 to 1 time is 2, 1 to 2 time is 3. Okay, that's the simple meaning of this line. You want to know in how many ways you can travel from intersection 0. Okay, so 0, it is going to be my source. Okay, we have to start from here only. Okay, so you want to know in how many ways you can travel from intersection 0 to intersection n minus 1. N minus means 6, from 0 to 6. Okay, 6 is nothing but my target or my destination. Okay, in the shortest amount of time. So we need to know how many ways you can travel. Okay, in how many ways you can travel from 0 to 6 such that you get the shortest amount of time always. Okay, so here first thing that we need to find out is the shortest time to reach from 0 to 6. Okay, that is going to be the first thing, shortest time. Okay, then calculate the in how many ways you can reach, how many ways you can reach from source to destination in that shortest time. Okay, we have to turn the number of ways you can arrive at your destination in the shortest amount of time, and since the answer may be large, we have to turn it in a modulo 10 to the power 9 plus 7. All right, okay, so I hope that you guys are clear with problem statement. Okay, so here first thing, okay, since this is a graph problem, so first let's create one adjacency list. Okay, so here 0 to 6 I am moving. Okay, so first of all n is 7, so I know that I have vertices from 0 to 6. Okay, so I can write that like this. Okay, 0. Okay, then from 1 we have some vertices. Okay, then from 2 we have some vertices. All right, then from 3 we have some vertices. Okay, then from 4 we should have some links. Okay, all right, I can say that, right? From 5 or from 6. Okay, so from 0 there is a path to 6. Okay, and here path is to 6, and here what is the total time that I'm taking? 7. Okay, so that's it. Okay, so 0 to 6 I'm moving, so definitely I can move from 6 to 0 as well, since this is a bidirectional graph. Okay, bidirectional roads are there, so 0 to 6 I can move, so 6 to 0 I can move. Okay, so here I can write 0 comma 7. Done. All right, after that 0 to 1 in a 2. Okay, so 0, after that you are moving from 0 to 1 in a 2. Okay, same way from 1 you can also move to 0 in 2 time. Okay, done. All right, then 1 to 2 in a 3. Okay, 1 to 2 you are moving in 3. Okay, then same way from 2 to 1 also you can move in 3. Okay, since this is a bidirectional road. Here 1 to 3 in a 3 or 3 to 1 in 3. Okay, both we have tried. Okay, so 1 2 3 here. Okay, 1 2 3 in 3. Okay, and then 3 to 1 in 3. All right, this is done. Okay, then after that 6 to 3 in 3. Okay, 6 to 3 in 3, and also 3 to 6 in 3. Okay, bidirectional road. Okay, 3 to 6 in 3. All right, this is done. After that pick this 3 to 5 in 1. Okay, 3 to 5 in 1. Okay, so first thing, this is what you need to do. Okay, create one adjacency list. Okay, so 5 to 3 also. Okay, 5 to 3 also in just 1. Okay, done. Then 6 to 5 in 1. Okay, so write this as well, 6 to 5 in 1, and definitely 5 to 6 also in 1. Okay, this is done. All right, now after that 2 to 5 in 1. Okay, so here write that 2 to 5 in 1. All right, and here 5 to 2 also in 1. Okay, then after that 0 to 4 in 5. Okay, 0 to 4 in 5, that also means 4 to 0 in 5. Okay, 4 to 0 in 5. Okay, done. Then after that 4 to 6 in 2. Okay, 4 to 6 in 2, that simply means that from 6 also you can move to 4 in 2. All right, so here now if you see, so we have created one adjacency list. Okay, so here 0, from 0 we are moving to 6 in 7, 1 to 2 and 4 to 5. Okay, and from 1 0 to 2 3 and 3 3. Okay, here same way 1 3 5 1, and here 1 3 6 3 5 1. Okay, so this is nothing but from 3 to 1 in 3. Okay, here we are writing 0 to 5 6 to 2, here we are writing 3 1 6 1 2 1, and here we are writing 0 7 3 3 5 1 and 4 2. Okay, done. So this is the first thing, we have to create this adjacency list. Okay, now after that here you want to move from this source. Okay, this is my source, and you want to reach here to my destination. Okay, so here can you do one thing here? Can you apply DFS here? First tell me, can you apply DFS? So what for DFS, what you are going to do? First you are going to go move to this this 0, and then from 0 you are going to pick the neighbor 6, and then from this neighbor 6 you are going to reach to destination. Okay, so you will take one value 7. Okay, then after that you will check other neighbors starting from 0 to 1 you can move. Okay, and then for this one you are going to check the neighbors like from 1, then you can take 2. Okay, so done. Then you are going to check the neighbors of 2. So from 2, let's say you move to 5. Okay, then from 5, then from 5 you can, let's say, move to 6. Okay, you can move to 3 also, you can move to 6 also here. Okay, so this DFS, it is going to be inefficient for this one. Okay, so we are checking all the possibilities, all the paths. Okay, and all the paths are not leading to the shortest path. Okay, the path with the minimum time. Okay, so it's very inefficient, right? So DFS would be highly inefficient because it would explore all the possible paths, many of which would be unnecessary since they do not guarantee the shortest travel time. Okay, so this is nothing but the brute force. Okay, brute force approach of checking all the paths using DFS would have an exponential time complexity. Okay, and it would be infeasible for the large inputs. Okay, so we are not going to implement GFS here. Okay, to calculate the shortest time. Okay, for reaching from source to destination. Okay, so here also, and one more thing here, you may ask, you go to from 0 to 6, and then from 6 you can again go back to 0. Oh, that is very bad now. Okay, so it's like A to B and C. Okay, you want to go from A to C. Okay, so it's like A to B you move in 2 times, and then B to C you move in 2 times, so you reach in 4. Okay, now here this is bad now. If I move A to B in 2, and then again I move back from B to A in 2, and then again I go to 2. Okay, then again move here, so we are not going to repeat the paths. Okay, so this is unnecessary thing. Okay, so that is why here if you see 0 to 1 I move, and then 1 to 0 I didn't use this. Okay, that's the purpose, that's the reason. Okay, in DFS also I directly check the second neighbor. Okay, from 2. Okay, same way there will be many paths. Okay, so DFS is not good approach here. Okay, now this is for DFS. Okay, so now after that, let's say can you apply BFS? Okay, so BFS also, it doesn't work for the weighted graphs unless we modify them with the priority queue. Okay, so which ultimately turns it into the Dijkstra's algorithm. Okay, so actually Dijkstra algorithm is best. Okay, so Dijkstra algorithm is the best fit for this problem because it efficiently finds the shortest path from the single source node to all the other nodes in a graph with edges that have non-negative weights. Okay, so non-negative weights we have, right? So the core principle of this Dijkstra algorithm is that, okay, that it always expands the currently known shortest path first, ensuring that when we reach a node we do that so in the minimum time possible. Okay, so let me explain the Dijkstra algorithm. Okay, but you guys already know that why we can't implement here DFS, brute force, and this BFS. Okay, so done. Okay, so BFS, why don't we implement? Because BFS doesn't work for the weighted graphs unless we modify that with the priority queue. Okay, so if we are using priority queue, that simply means that we are using Dijkstra algorithm. Okay, so Dijkstra algorithm is nothing but is a greedy algorithm that uses a min heap priority queue to process nodes in increasing order of their shortest known distance. Okay, so what you need to do now? Okay, so we have already created this adjacency list. Okay, so now here uh, do one thing. Okay, so for Dijkstra's algorithm you have to create we have total 6 vertices. Okay, so here let's create a array. Let's say this is one array and this is one more array. Okay, two arrays we are going to create. Okay, and here now here we have 6 vertices. Okay, so 0 1 2 3 4 5 and 6. Okay, so let me just draw this. Done, 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 done. Okay, and here also 0 1 2 3 4. Okay, 5 and 6. Okay, so what are the two arrays that I'm creating here? So one is shortest time. Okay, so this array you can say here shortest time. Okay, done. And we are going to create one more array that is nothing but you can name it as you can say this as maybe here we are taking it shortest time, so here you can take it as path count because we have to count the path as well. Okay, so here let's say path count. Okay, done. So we are getting two arrays, one is shortest path, okay, and one is path count. Okay, and you know that here we have to take that in a long. Okay, because maybe we'll get very big values. Okay, here for the time. Okay, so I will take that in a long. All right, so here 0 to 0 you can reach in 0 minutes. Okay, 0 time, right? So here I'm writing 0 initially for this one, and 0 to 1 I don't know, so initially I just updated everything to infinity. I don't know here, I don't know infinity. Okay, it's taking a lot of time, I don't know. Okay, now path count. So 0 to 0 there is only one path now, in just one way you can reach from 0 to 0, that's it. Okay, all right, now here 0 to 1. Okay, so here 0 to 1 we have to update, 0 to 2 we don't know right now. Okay, so here all this stuff we don't know. Okay, so I'm going to fill all this stuff. All right, so now what you need to do? Okay, so after that, so here I will just update this path count of at 0 index as 1, and everything else I will not update anything. Okay, I will remain as it is. Okay, so now after that, once this is done, okay, so initially all this is 0, I don't know. Okay, so you can say 0 0 0 0. Okay, don't get confused why I'm not writing anything here. So 0 0 0. Okay, all right, so now here after that you see first time from 0 we can move to 6 in 7. Okay, so okay, one more thing here, you can create one let's say this min heap. Okay, min heap also we need now. So here min heap, let's say this is my min heap. Okay, so here this is min heap, min heap. Okay, so now how we are going to store the things in min heap? Okay, so initially in the min heap I'm going to add 0. 0 is nothing but the time. Okay, and here I'm adding 0, that is node. Okay, so to reach node 0, okay, node 0 I am taking this much time. Okay, so from here my priority queue will start. Okay, 0 0, done. Okay, so now I will run one while loop, okay, and in the while loop I will check while my mini heap is not empty. So right now my mini heap is not empty, right? So now from I will just poll this element, okay, I am going to poll this element. So I will poll this 0, 0 and 0, okay. So now here from this 0 you can move to 6 in 7, okay. So 0 to 6 you are moving in 7, okay. So here it is infinity now, so let's just update it to 7 because we can move from 0 to 6 in 7, okay. So here what I will do, I will update this as 7, okay. And now 0 to 6 there is one path, okay. So here I will update this value as this value, okay. So from here the value is 1, okay. So to reach 0 there is just one path, okay. So now in this path, from this path only I am reaching to 6, right? Okay, so that's why I'm going to add this value, okay. So here let's say this is one position and this one, but this is one position. So to reach here you have total two paths, so definitely you are going to write 2 here now. To reach here also you have two paths now, you can follow this, you can follow this, okay. So that is why this value I'm adding it here, okay. This is one, so I'm adding it here, okay. Done, okay, done, okay. So this is clear, right? So now this is done, okay. So here I will add now that I am reaching in 7 time, okay, in 7 time, and to which node, I to node 6, okay. So in this min heap I will add like this, okay. So this is min heap, so smaller time will go to the top only, okay. So done, okay. Now after that what are the other neighbors of 0? So 0 to 1 I can move in 2, okay. So 0 to 1 I can move in 2, okay. So here I will add 2, okay. 0 to 1 I am moving in 2, okay. And now there is also one path here, so here I will update this, okay, to 1. So in time 2, I am moving to 1, okay. So here I will write 2 and 1, okay. And here you can remove this now, I actually poll this, okay. I remove this element first, okay. Now what are the other neighbors of this 0? We process this, now 0 to 4 I can move in 5, okay. So 0 to 4 I can move in 5, okay. And here also there is one path, okay. So I will just add from 1 to 4, okay. So here I will add 1 only, done, okay, clear, done. And also 0 to 4 I am moving with 5, okay. So here I have tried 5, okay. So here you have to add 5, and okay, let me just do one thing here, let me just keep it top, okay. 2 and here 1, all right. So now here what I'm adding 0 to 5, okay. 0 to 4 we are moving in 5, okay. So here I have to write time first and then I have to write 4, okay. Done. So this is done, okay. This one cycle is completed. Now after that I have to process what, I have to process this node 1, okay. So this is at the top of my min heap, so I have to process node 1, okay. And in node 1 I am reaching in time 2, okay. In node 1 I am reaching in time 2 to this node, okay. So now here let me just erase this, okay. So you are clear, right? Now just remove this topmost element and we know that we are reaching to node 1, okay, and 1 node 1 in time 2, okay. Now after that here see 1 to 0 I am moving in 2, okay. So until 1 I am taking 2, okay. And from here I am moving back to 0 in time 2, okay. So here this time is 2 and here this time is 2, okay. So 2 plus 2, 0 to 1 2, okay. Then 1 to 0 I'm moving back, so 2 plus 2 4. But here it is minimum now, don't update, if it is minimum, okay. So we are not going to update it, done. We are going to continue, we are going to skip this, okay. Done, okay. This is done, all right. Now 1 to 2 I can move in 3, okay. 1 to 2 I can move in 3. So here what I'm saying, 1 to 2 I can move in 3, 1 to 2 I can move in 3. So that simply means here in this infinity sign, okay, we get the minimum time now, that is nothing but 2 plus 3, this 5, okay. So this is what we get, and also here there is one path, okay, 0 to 1 and 1 to 2. Okay, so here this value is 1. Okay, so this is what I have to write, the same thing here. Okay, this is done. Okay, now here what I have to do, I have to add this. Okay, so I am reaching in a time 5 to my node 2. Okay, so here 5 in a 2. Okay, so here initially it was 5 by 4. Okay, and here I will update 5 in 2 I am reaching. Okay, so in time 5 I am reaching to node 2. Okay, done. I process this. Now I am saying that in from 1 to 3 I am moving in 3. Okay, so 1 to 3 I am moving in 3. 1 to 3 in 3 I am moving. So here I have to update 5. Okay, and now here I have to update 1. Okay, because from 1 to 3 I am moving, right? So this is done. Okay, this is done. So here also I will write that in time 5 I am moving to node 3. Okay, so I will add that here. Okay, uh, here I will add, okay, here 5 and 3. All right, this is done. Okay, we have processed this. Okay, so this is done. All right, so now after that in the top we have node 4. Okay, node 4, and to node 4 I am reaching in time 5. Okay, done. Okay, so now just remove this from the top. Okay, and now in my array, in my this min heap, we have 5 comma 3 and 5 comma 2, right? These two are there. Okay, so let me just erase it. Okay, these two are there. All right, so now here let me remove this as well. Okay, so now here node 4. Okay, node is 4, and here time is 5. Okay, okay, node 4, check node 4. From node 4 if I can, I move to 0. So from 4 I can move to 0, but here I'm taking time 4 to 0 in 5. Okay, so here it is taking 5. So here also it is 5 now. I am reaching here at to node 4 at 5, and again I'm adding 5 10. So this is minimum, I don't need to update. Ignore this. Done. Ignoring this. Okay, then here 4 to 6 we can move in 2. Okay, so 4 to 6 we can move in 2. Okay, so 4 to 6 you can see that we are moving in 2. Okay, here one thing, see clearly, 4 to 6 we are moving in 2. So that simply means that I am moving from, I will get one more 7 here. That simply means there is one more path, right? See here in this 5, if I add 2 I will still get the same 7. Okay, here it is already 7. That simply means that there was one way in the starting when I reached to 6 at 7. Now there is one more way, because here I am starting from 4 now. There is one more way, and in this way also I am reaching to this position as 7 only. Okay, so now what we have to do in that case, we have to update the path count. Okay, so I'm going to update the path count as, but is the path count of my neighbor node. Okay, that is this one, it was previously, and now this. Okay, so 1, and this was 1 before. Okay, 1, and in this one I'm going to add this one, so I will get 2 here. That simply means that there are 2 paths. Okay, clear? All right, clear. Okay, so now here this is done. Okay, so now this time I'm not adding this in my min heap. Okay, I'm not adding this thing in min heap. I'm only adding that in my min heap. Then when my current time, the plus the row time, okay, whatever the total time, if it is less than the shortest time of the neighbor node, okay, only then I am adding that in min heap, otherwise I'm not adding. Okay, so this is done. Okay, now here this is done, this is done. Okay, so now we process all the neighbors for this one. Okay, so now again you have to remove this. Now we are going to remove the topmost. So to my node 2 I am reaching in 5. Okay, to my node 2 I am reaching in 5. Okay, to my node 2, okay, let me change it to 2. I am reaching in 5. Okay, all right, so from 2 we have to start checking out. All right, so 2 to 1 I can move in 3. 2 to 1 it is saying, what I'm saying here, from node 2 we have to check now. Okay, from node 2, so from node 2 it is saying that we can move to 1. Okay, so node 2, this is the node 2 now, not this one.
Okay, this is the node 2. Okay, so from this node 2, that simply means this is my source. Okay, for right now, so from 2 to 1 I can move in, it is saying 2 to 1 you can move in 3. Okay, so here if I do this, so 5 plus 3 8, but I don't need to update now. This is minimum only. Okay, I don't need to update. Okay, then here after that I processes 2 to 5 you can move in 1. Okay, so let's see, 2 to 5 can I move? If I move in 1, okay, that's it means 2 to 5 I am saying that I can move in 1. Okay, so that simply means that 5 plus 1, so here I am reaching in 6. Okay, here I am reaching in 6. Okay, 2 to 5 in 1, that simply means 5 here plus 1 6. Okay, in 6 I am reaching to the 5. Okay, so here we have to add now. Here we have to add, so here I'm adding 6, and to 6 I'm reaching in 5. Okay, 6 is nothing but my time, and then I have to reach right the node. Okay, and also here there is one path now from 2 to 5 now, so here 0, so just update this. Okay, 0 plus 1. Okay, or you can take this only, because this is the first time we are encountering the minimum value here, that is why we have updated, right? So here I'm writing 1. Okay, all right, so when we get any minimum value, okay, here it was same value, then we do the addition. But if we get some smaller value 6, then we have to update it to the previous one only. Okay, then we don't have to do the addition. Okay, so done. So we process these twos 1 and 5, done. Okay, now again from 5. Okay, time is 5 from 3. Okay, so let's see, and here let me update to 3. Okay, and we have to remove this topmost. Okay, 5 3. Okay, and here let me just bring this 6 and 5 here inside this. Okay, now it looks good. All right. Okay, so to node 3 we are moving in 5. Okay, so from 3 we have to start. Okay, so this is my start. Now from here I will just check. Okay, so here from node 3, if you see, uh, we can move to 1 in 3. Okay, so here from here we can move to 1 in 3. So 5 plus 3 8, skip it, no one required. Okay, then to 3 to 6 in 3, 3 to 6 in 3, 3 to 6 in 3, that is also not good now. Here 5 plus 3 8, this is also not good. Okay, then 3 to 5 in 1. Okay, 3 to 5 it is saying in 1. All right, see here, now 3 to 5 we are moving in 1, but here both are same. Okay, so 5 plus 1 6, and this 6 is already there, so here I will update to 2. Okay, because 6 was already there, there was already one path with the 6. Okay, now again we are getting 6, so here I'm updating it to 2. Okay, that's it, but this time we don't have to add this in my main heap. Okay, done. So we have processed this. Okay, now after that, now let me just remove this, remove this, remove this. Okay, now after that, uh, to my node 5. Okay, to my node 5 we are moving in time 6. Okay, so 6 here. Okay, so from 5 we have to start. Okay, so from 5, if you see here, from 5 we can move to 3 in 1. 5 to 3 to in 1, so I will get 6 plus 1 7, ignore it. From 5 we can also move to 6 in 1. Okay, so 5 to 6 in 1 you are moving, that simply means that 6 plus 1 7, so again you are getting 7. So if you are getting the same value, so then what you need to do, so from here, from this 5 you have to pick this 2, and in this 2 you have to add this current value, so 2 plus 2, so you are going to update it to 4. Okay, and then we don't have to add this in my this min heap, right? So this is done. Okay, then from 5 to 2 you can also move in 1, so 5 to 2, if you see this. Okay, here, so in 1, so total 617, so we don't need to update. Okay, that is done. So here we have processed this as well. Okay, now in the end we have to process this 6 node with the time 7. Okay, with the time 7. So here you will again calculate everything. Okay, so here like this. Okay, so from 6 you have to check 6 to 0, so that is also not going to give the best result. 6 to 3 also you are going to get 10. Okay, you are not going to update. Then 6 to 5 also you are going to get some bigger value. Okay, you are not going to update. Then here, from here also you are going to get bigger value. Okay, so now in the end we have processed all this. Okay, and our main heap becomes empty. So now if our main heap becomes empty, we have to stop. Okay, so now from 0 to 6 we are moving now, so 0 to 6 we are moving. So here see, in the path one we have already calculated the 4 paths. Okay, and that is correct. Okay, so 4 paths are there. So output is 4, and see 0 to 6 one path, 0 to 4 to 6. Okay, there is one path. Then here 0 to 1 to 5 6. Okay, 0 to 1 3 5 6. Okay, so this is clear, right? Okay, so here see, if you want to check until 5 here, so until 5 here, so you see total 2 paths you are getting here. So until 5 here also I've saved 2. Okay, so this is the best algorithm. Okay, right? Dijkstra algorithm to solve this. Okay, so now let's write the code is going to be very simple, same story that I've explained just right now. Okay, so if you guys want, you can pause the video and start writing the code by your own. Okay, and now I'm moving to the coding part. Okay, so here first thing that you have to do, so since in the problem statement is given that values can be very large. Okay, so here just create one mode variable int mode. Okay, and here I will store 1 1 2 3 4 5 6 7 8 9. Done. Okay, then after that, here if you see what we were doing, so we are creating a list of int arrays. So this is a list of int arrays. Okay, these are the int arrays, so list of int arrays, and I can say that this is at 0 index. So this is like this, list. Okay, and inside this, but we have more lists. Okay, more lists. So more lists like this. So this list is at 0 index, 1 index, 2 index. Okay, from index basis I can get so inside this list we have lists, and these lists, what this list contains, this list contain int arrays. Okay, int arrays. So see here, these are the nothing but arrays. Okay, 6 7 1 2 2. Okay, so this is what we need to do. Okay, so here list of int. Okay, and you can say here graph. Okay, and here new array list. Done, right? And then after that, run one loop. Okay, for int I is equal to 0, I is less than n, I plus plus. Then after that, we are going to take this graph. Okay, so here writing graph, and in the graph I'm just going to create the new array lists. Okay, new array list. So once this is done, so we have created the array lists. Now after that, I have to put all the values. Okay, I will have to iterate over the rows, and I have to put all the values in my adjacency list. Okay, or this graph, right? So for each loop we can use, okay, int road in roads. Okay, and now after that you can take a start node. Okay, start node. Okay, and in the start node you are just going to pass a road of 0 value. Okay, now same way you can copy this. Okay, copy this, paste it here, paste it here. Now this time here road of 1, so here you can say this is nothing but end node, and now after that you can also take travel time. Okay, so this is nothing but travel time. So here you can write travel time. Okay, and here you have to write a road of 2. Okay, now after that, how we have to add the values? So from the graph we get that particular value of start node. Okay, start node, and in that start node value we have to add what? We have to add the array. Okay, so here new int, and in this array what are the things that we are going to pass? We are going to pass here end node. Okay, and here we have to pass travel time. Okay, this is done. Okay, now just copy this same line, copy this and paste it here. So now it's a bi-direction road. Okay, so we have to update end node as well. Okay, so again node dot add, here you have to write a start node, and here you have to take the travel time only. Okay, so this is done, right? So now here you have to write priority queue logic, priority queue. Okay, in priority queue what do we have? We will have the two values. One is that particular time in which we are reaching to that particular node. Okay, so time and node are there. So here I will take long. Okay, long array. All right, so here let's name it as min heap, okay, min heap, and here new priority queue, okay. Inside this, this is going to min heap, okay, and based on their time we have to sort, okay. Less time will go on the top, okay. So here inside this, what I'm going to write, I'm going to use comparator, okay. And here what I'm going to compare, so since I'm using long, so here I write comparing long, okay. And let's suppose that I have one parameter a, so in that parameter, based on the first value, okay, the value at a of 0, I'm doing this min heap, okay. I'm sorting the elements, okay. So a, and here a of 0 we have to write, okay, first index element based on that, right? So now this is done. Now after that, you have to create two arrays as well. So long, so here shortest time new long n, you can say, right? And then after that, initially you have to fill all the with max value of long, okay. So we initially we don't know the paths, okay. Only for the first one we know the path, right? So others we have to fill now. So here I will write first arrays dot fill shortest time, and here I will write long, L should be capital na? Long dot max underscore value, all right. So this is done. Now we have to calculate the paths, okay. We have to create the array for path count as well. So here you can write int path count, okay, int path count, all right. And here you have to write new int, okay. And here you have to write n only. And then shortest time, you already know, for the first, what is this, okay, it will be 0 only, okay. We are already starting from there only now. So let's suppose the path count, okay, to reach at 0 is just 1, okay, in the starting, all right. So now after that, in the min heap, in the starting, we have to offer something, right? So in the min heap, I will say that in the min heap dot offer, I will just pass one array of new long, okay. And here inside this, I will pass 0 and 0. So what are these 0 and 0? So these 0 and 0 are nothing but my time to reach node 0, okay. So here time and node, okay. So this is what I have here, okay. So this is done. Now after that, I will run one while loop while my min hoop is not empty, okay. So min heap is not empty, okay, while my min heap is not empty. So until then I have to do this, okay. Now here inside this, we have to poll the topmost array, okay. So here I will create one array long of top type top, and here I will just write min heap dot poll, okay. So here in this top array, we are using two indexes. So first, you can say first is current time, so it will be in I have to write in long format, okay. Long c should be small, okay. Scar time, and here you can say top of 0. And these node values, I can say I want to in int, okay. So cur node is equal to, I will just change that to int. So here I'm just using int, okay. And then here I will use top, okay, and here 1, okay. So this is done, okay. So now we get the current time and the current node, okay. So now after that, we have to skip the outdated distances. So I have already explained what are the outdated distance, okay. So where let's suppose initially time is infinity, then after that we are getting some other value, then we are using. But if to reach that particular node time is 2, but now we are getting 5, so then why do we need to update that, okay. So that's what, okay. If cur time, okay, if cur time, if it is greater than shortest time, okay, for to reach that particular cur node, okay. So in that case, we have to just simply continue, done, okay. Then here after that, we have to iterate over all the neighbors, okay. For int uh, neighbor, NEIGHBOUR, you can use a neighbor computer word, right? So here graph dot get, okay. And here you have to pick that particular kernel node, and from that kernel node you have to check the neighbors, right? So here after that int neighbor node, okay, so it is going to be a neighbor of 0. All right, then the road time, okay, so int road time you can say, and here you have to write neighbor of 1. Okay, at 1 we have this. Okay, so this is how we are storing, right? So now we have to find a new shortest path. Okay, and then we have to update the shortest time and reset path count. Okay, all that stuff. So here I will just write if cur time. Okay, so now understand carefully here. Okay, if in this cur time I'm adding the new road time, okay, that we have. So if I get this value smaller than the shortest time, okay, the value that is already stored in there my array. Okay, shortest test shortest time. Okay, and here I will just pass neighbor node. Okay, so here I will just check the time. Okay, so if it is less than this, okay, then in that case we have to update this shortest time neighbor node. Okay, this value, let me just copy this. Okay, shortest time neighbor node, I will just update it with current time plus road time. Okay, so this is the new minimum, right? So I have to update like this. Okay, now if I am updating this, okay, so that simply means that I am finding the shortest time for very first time. Okay, so in that case we have to update the path count as here path count as of neighbor node neighbor node neighbor node. Okay, I have to update it as path count. Okay, previous count from where we are moving. Okay, from there. Okay, so path count of current node. Okay, so this is done. So this is going to reset the path, okay, for that particular minimum. All right, so this is done. Okay, so this I already explained somewhere, I think. Yeah, this one. Okay, this logic I explained from uh, here you are a b c. Okay, so at a you are reaching in 2 ways. Okay, so now you get the minimum time here 6 something. Okay, from this point, so that simply means that you can also reach from 3 ways only, 1 2 3, these 3. Okay, you can move this way, then this way, this way. Okay, that's it. All right, so this is done. Now this time we have to add this in min heap. Okay, so min heap dot offer, and here new long. Okay, and here you have to write what you have to write a shortest time of neighbor node. Okay, so you can copy this shortest time of neighbor node, and then after that you have to pass neighbor node. Okay, so you can copy this and you can paste it here. Okay, this is done. Okay, so two things we are passing every time in the main heap. Okay, first is the shortest time in which we reach to that particular node, and the particular node value, right? So that's what. Okay, now in the else if part. Okay, so in the else if, so now inside this, if this current time plus road time, okay, if it is greater than that doesn't make sense, but if it is equal to, then we have to update, right? So if it is equal to, then we were doing the addition. Okay, from where it is coming to the existing value. So here then in that case we have to write path count of neighbor node is equal to path count of neighbor node. Okay, and plus the path count of current node. Okay, so you can write it like this. All right, so this value could be maybe very large. Okay, so you have to write like this: path count of neighbor node plus path count of current node, and just keep everything here like this, and do the mode with mode. Okay, so here mod, okay, the variable that we have created in the starting. Okay, mode. So that's the purpose of this. And now in the end you have to just return, that's it. Okay, return. Here you have to write path count and n minus 1. Okay, now let's run it and see if the code issue. Will try to fix that. So yes, there are some issues. So here current time plus road time are 2 equals to. Okay, we are not assigning value, we are just comparing. So 2 equal to should be there. All right, So now all the test cases has been accepted. Wonderful. Now let's submit it. So see, our solution is accepted, right? So I hope that you guys are able to understand today's problem. And if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.